Try solving this equation. Are you thinking, should I factor it? Use the quadratic formula? Transform it somehow? But what if I told you no factoring, no formula, no transforming, no tricks? You don't even need to analyze the structure of the equation. Just pick any number, literally any number, plug it in, and the solution reveals itself. Not just a solution, all of them. Let me introduce the secret method most people are missing. Follow along. This is the formula which is called the Newton-Raphson method. It's usually taught as a way to approximate a solution. Try your guess, run the formula, and it gradually reveals a solution. Let's apply it to this quadratic. F prime of x equals 2x minus 5. Let's try x0 equals 10. We compute x1 equals 6.4, x2 equals 4.73, x3 equals 4.12. Look at that. It's closing in on 4, one of the roots. The value it converges to is the solution. But what about the other one? Let's try x0 equals minus 10 this time. We get x1 equals minus 3.84, x2 equals minus 0.84, x3 equals 0.48. It quickly converges to 1, the other root. Surprisingly, you can steer Newton-Raphson to different roots simply by changing the initial guess. Different guesses, different basins of attraction, different roots. But be careful. What if f prime of x equals 0? In our case, that happens at x equals 2.5. It doesn't work, because f prime of x is in the denominator of the Newton-Raphson formula. So avoid the point where the derivative vanishes. What's interesting is this. Pick a number less than 2.5, and the estimate converges to 1. Pick another number greater than 2.5, and the estimate converges to 4. That point x equals 2.5 acts like 0, separating two parts. Now let's level it up to a cubic. F prime of x is this. Try different guesses. x0 equals minus 10 converges to minus 2. x0 equals 0 converges to 1. x0 equals 10 converges to 3. All the roots emerge, no factoring needed. The key? Choose diverse initial guesses that fall into different zones. Mathematically, there are two critical values where f prime of x equals 0. The values are complicated. They split the number line into 3 basins of attraction. Pick a guess less than this, you land at minus 2. Pick one between this and that, you go to 1. Pick one greater than that, you reach 3. Now, you've got a powerful tool to solve equations. Congratulations! You can apply it to any equation. Let's go back to the very first equation we saw. F prime of x is this. Let's try x0 equals 10. At first, it seems to be heading somewhere. But soon, things get weird. It doesn't converge. What's going on? Let's check the discriminant. It's negative. A negative discriminant means no real roots, only complex ones. Here's the surprising part. Newton-Raphson itself gave us a clue. When it refuses to converge from any real initial guess, that's a strong hint. That equation has no real roots. So in a way, Newton-Raphson doesn't just find roots. It helps us detect whether real roots exist at all. Let's try something new. Start with a complex guess. x0 equals 10 plus 10i. Watch what happens. The real part moves toward 3. The imaginary part toward 1. It converges to 3 plus i, one of the exact roots. Now try x0 equals minus 10 minus 10i. It converges to 3 minus I. Yes, Newton-Raphson isn't just for real roots. It works in the complex plane too. But its power doesn't stop there. Let's try a few more. Not harder, but awesome. The first equation is this. 1 root is 1/11th, or repeating decimal. Let's start with x0 equals 10. You'll see the estimates converge to 0.09 repeating. Beautiful. Now try this equation. 1 root is root 2, irrational. Start from x0 equals 10 again. The estimates converge to 1.4142, which is the actual value of root 2. Newton-Raphson doesn't care what kind of number you're after, rational, irrational, or even imaginary. If it's a root, you'll find it. Newton-Raphson is about approximating the solution, but today we've seen its real potential, a bridge to every root. Newton-Raphson requires many calculations, but that's no problem for computers. That's exactly why it's still so widely used today. In fields like computer graphics, machine learning, and robotics. Did you enjoy this math traveling? Please subscribe for the next trip.